Okay. Get started.
Okay. All right, welcome everyone. What a wonderful and warm turnout for a defense on a kind of an early morning for a Wednesday for summer. So thanks to all of you for being here. There are many friends in the audience, supportive colleagues. We even have some returners. Professor Robert Soden is here. He graduated just a couple of months ago. And Professor Maria Kogan surprised me. And she graduated a year ago, year and a half ago?
A year and a half ago.
Something like that. Okay, so, we have Townie, Jennings' father here, which is wonderful, and friends and colleagues. So I'm Alicia Palin. I am the advisor, primary advisor for Jennings, and I always enjoy, this is always an exciting moment when we get to this point. And I also get to introduce him, and I take a little bit longer to introduce so I can tell a little story about how somebody kind of came to this point, which you might not know about, which they may not share, but I don't think it's embarrassing. So I'm really honored to introduce Jennings Anderson. Jennings came to us from Carroll College in Montana after majoring in computer science. It's a small college, really excellent one, but in computer science, he didn't have any exposure to human-computer interaction or studies or computer-supported cooperative work, sort of empirical techniques to thinking about the relationship between computing and society. And so he ended up coming here, and he was temporarily associated with our lab because I really saw a lot of potential in him, but I wanted him to be able to have a chance to explore other parts of computer science. Well, he arrived in August 2013. If you were here in 2013, I think Robert arrived that very same time. The Colorado floods were a really, really big event. And so within 2 weeks of his arrival, he was simply doing research on extracting usable data from social media to supply to the Colorado Department of Transportation to do real work in the flood recovery. That led to a set of collaborations with professors in civil engineering here, environmental design, professors and students there, and of course in computer science, and resulted in publication too, with 3 Andersons, Anderson, but no relation to any of that. So that was, I think, a very exciting start. Now, I'm not sure what went through his head at the time. Maybe he'll share that with us. But from my point of view, he kind of really became dedicated to the role of data analytics and software engineering development in pursuit of difficult and empirical practical problems at that time frame. And it was at that point that we saw very early on kind of a real immersion in the work that the lab was doing. And he's done a lot of work that you won't hear reported today because it's sort of outside the dissertation, but has participated in a number of publications that have been well received in a number of areas outside of OpenStreetMap. He came to work at OpenStreetMap because of the collaboration of Robert Soden, who brought that kind of sensibility and expertise here when he also joined us. And so that's what you'll hear about today. So one of the things that I enjoy hearing his committee talk about is how he has the rare talent of being able to go out and combine software engineering abilities and think about the problems of software engineering as they relate to data science issues, and as those are then attached to real world questions that have true empirical value around human behavior. And that's really hard to string all those things together and to develop enough expertise in all of them to be able to intelligently work in that space as a kind of union of things. What he then does is he listens to the empirical work that he or others are doing and feeds that back into thinking about the design of the software engineering applications and the analytics that might yield itself. And so I think you're going to hear that today, and I think that's, to me, the most exciting thing about the work. So finally, another hallmark of a true scholar is one who willingly collaborates and contributes his expertise to others. And he certainly does that with many people here in this room. He does it with ease, and so as a result of that, he has a worldwide network of folks who are working in this space that he's working in, and I can see very much that he has made contributions and also has been impressed upon by those who are really working at the frontiers of these problems in ways that I think really powerfully move the research forward. So That's one of the other things I appreciate about him very much. So that's Jennings. I will let him speak in a minute. I realize I should do some logistical stuff first. I should introduce his committee. So first we have from all the way over the pond, João Porto de Albuquerque, who's at the University of Warwick. He's dialing in and he is attending to the slides here, and we'll hear from him at kind of questions. João, do you want to say a little hello?
Hello everyone.
Hi.
Thanks a lot for the invitation. Pleasure to be virtually here.
We're really grateful to have you here. Thank you so much. Tom Ye is also on Jennings committee. Ryan Keegan is here from Information Science, also on his committee, and Ken Anderson, who has been a co-advisor on some of the software engineering parts of this work, especially the early parts of this work. So thanks to all of you. What will happen is Jennings is going to give a seminar-style presentation. Will be about 50 minutes long. Then, because we're in this multi-purpose space, what we tend to do when we hold defenses here is, and because we have a total constraint 2-hour window for the committee, which is standard also for those of you who have yet to go through this, we have the committee ask the questions first. We usually have the person who's dialing in from a distance go first, because sometimes they have a hard time hearing what's happening in the room. So João will ask questions first unless he decides to defer. Then we'll have the committee ask questions. Then, depending on the time, we will have questions from the audience while the committee is present. If we feel that we don't have enough time to then do our deliberations in the back room, the committee will excuse itself, go have deliberations in the back room, and the audience, you can continue asking questions of Jennings or celebrate or do whatever you want to do after we go. So that's the order of business. Does that sound okay?
That sounds good.
Okay. All right, so Jennings Anderson.
Yeah. All right. Thank you all for being here this morning. This dissertation is titled Contributor-Centric Analytics for OpenStreetMap, Approaches to Full-Stack Metadata-Driven Analysis Infrastructure for an Open Data Geospatial Platform. A big mouthful, but let's just dive right in to what this is. So this is OpenStreetMap, as rendered on OpenStreetMap.org. As you can see, it's an interactive map. As we zoom in on campus, we see more detail. What separates it from the rest, however, is that it's editable. Clicking this edit button will launch an in-browser editor where we can see the features over satellite imagery. Clicking on this building will show the editable details and tags on the left. These include the name, address, a brief description, and other physical attributes of the building. CU campus is fairly well mapped. You can see that people have marked the grass, trees, benches, bike racks, and more. This is a mapper digitizing roads by drawing over satellite imagery on OSM. This is also referred to as armchair mapping, where this mapper isn't on the ground surveying or even in the area. They're editing the map remotely. The availability of high-quality satellite imagery makes this the most popular form of mapping in OSM. Anyone, anywhere in the world can now edit. So here's a rendering of all the roads in OSM as of 2017. Broadly, we see pretty global coverage with incredible density in Europe, where the project was started in 2004. There are over 5 million registered user accounts on the platform, 1 million of which have made an edit to the map. For many parts of the world, OSM is the best or only source of geospatial data. And OSM data is used in time and safety critical situations, such as disaster response. Apple, Facebook, Uber, Amazon, and many more companies contribute to OSM and or use OSM in some capacity. So that was OSM as an editable, interactive map. But OSM is more than that. It's an active online community. Understanding the map then first requires understanding how the community builds this map. So let's look at the complexities introduced when viewing OSM as a geospatial database that is collectively produced by this community of 1 million different contributors. This is what OSM data looks like in terms of geographic coverage. Yellow and green show areas that have seen a lot of mapping. This means many, if not all, of the buildings, roads, and various points of interest are mapped. Blue and purple, on the other hand, represent areas with very little coverage. Maybe a few buildings, a road, name of a town. This lets us know something is there, but it's far from being completely mapped. OSM is not immune to the participation inequality found in online communities. While over 1 million contributors have edited the map, about half of those have made more than 10 changes, and less than a third have made more than 100 changes. Only a few thousand contributors are responsible for the majority of the features mapped. There are many reasons that people contribute to OSM. I'll go into more detail about these contributors in a minute, but know that OSM contributors can wear many hats. From hobbyists and local mappers who map their hometowns to mappers who edit OSM as part of their paid profession. And OSM is a massive spatial database with over 800 million distinct objects on the map and another 1 billion revisions to these objects. So this adds computational complexity to working with this data. To summarize, these are the aspects of OSM that make data analysis a difficult, multifaceted problem. However, it's important that we have methods to understand how both this map and the community behind it evolves. OSM is no longer a localized hobby mapping effort to compete with difficult-to-acquire government-owned mapping data. Today, it is a community of millions of people producing data that powers many of the digital maps we interact with every day. The data is used to support disaster response and humanitarian relief, and in many parts of the world, it's the only map. OSM is more than just a database of spatial information, and there's more than just spatial information in the database. We can capitalize on the latter and embrace these complexities to better understand the map as a whole with what I'm calling contributor-centric analysis. So this means viewing OSM not just as a map, but as the collaborative product of more than 1 million contributors responsible for billions of edits all over the globe. To do this, we need to reimagine our approaches to OSM data analysis to prioritize the metadata about the edited map, tracking who made what changes and when and where so we can break down how the map evolved. So now that I've introduced OSM and broadly described the complexities and the problem I set out to solve, here's what's to come. For reference, these parts also map to the layout of the dissertation document itself. Next, I will describe a few of the types of contributors within OSM, the ways in which they map, and then dive deeper into the nuances of analyzing OSM data. Part 2 introduces the first analysis system we built here at CU called Epic OSM. Part 3 will then discuss the advantages of vector tile-based analysis and what it can do for contributor-centric approaches. Part 4 will discuss the implementations of tile-based historical analysis with snapshots of OSM over time. And Part 5 introduces the final implementation of full history tile-based analysis, the work it has supported, and plans for the future. But first, let me position myself in this space. I've been working with OSM data since 2013, building analytical tools that help us uncover the evolution of the map and the community. Throughout this time, I've been active in the OSM community, including mailing lists, participating in online conversations, attending both US and global annual conferences. Additionally, I helped organize the 2017 State of the Map US conference here on campus, as well as a workshop last fall in Detroit. I did 2 summer research fellowships with the company Mapbox focused on OSM data analysis, and all of the charts and figures you will see were generated from the systems that I will describe. Unless otherwise noted, the screenshots and animations of interactive tools are all systems that I've built or collaborated in building. So now let's explore the OSM contributors. This graph shows the lifespan of all 1 million contributors to OSM. The bottom axis here is the date of a contributor's first edit, and left here the date of their most recent edit. This concentration of purple across the top represents mappers who have been active for more than 21 days on the platform, and you can see that their latest edit was recent regardless of when they joined. The heavy concentration of yellow along the diagonal represents the opposite. These are the 1 or few time contributors whose first day of mapping is the same as or very near their last day of mapping. And the orange and red near the diagonal represent mappers who join and then map for 10, 20 days straight and then don't come back. So if we zoom in on 2015, we see this anomaly in late April. Mostly in red and orange, this cluster is comprised of many users joining and immediately doing a significant amount of mapping, but many haven't returned since. These contributors are engaging in disaster mapping, where many digital volunteers come together on OSM to trace satellite imagery to improve the map for an area experiencing disaster. In this case, they're responding to the 2015 Nepal earthquake. The largest group that organizes these mapping activations is the humanitarian OpenStreetMap team. Globally, if we subtract all of the edits not associated with the humanitarian OpenStreetMap team from the total edits to OSM, we see that since 2015, humanitarian mapping in OSM comprises a significant amount of the increase to the general editing activity. Another complexity of OSM is that these types of figures can drive a little bit of a divisive narrative. There are not fixed lines between these many communities. The same contributor may work on both humanitarian and non-humanitarian mapping. So this figure is merely showing that humanitarian mapping has a major impact on the map overall, not necessarily that humanitarian mappers are the most prolific in OSM, though that can certainly be the case during a disaster event. Researching this phenomenon of disaster mapping is how I was introduced to OSM. Specifically, this was to study the response to the 2010 Haiti earthquake, the first disaster mapping activation. In January 2010, nearly 500 volunteers created the most detailed digital map of Haiti in existence by tracing satellite imagery. This is a rendering of that activity over the 2 weeks following the earthquake. And this event really inspired this now global form of humanitarian response. 3 years later, Typhoon Yolanda struck the Philippines. This animation shows the work of about 1,500 volunteers tracing primarily buildings and roads from satellite imagery. These data were then used for damage assessment and recovery. In April 2015, about 8,000 volunteers responded to the Nepal earthquake by tracing thousands of kilometers of roads and hundreds of thousands of buildings. You can see the mountainous geography reflected by the shapes of the roads being traced here. So these are roads to villages and buildings within that are literally being put on a global map for the first time. Another community within OSM is that of craft or hobby mappers. I also add localized mapping to this group. I say localized here to mean that a mapper's work is focused on a local area or areas, not necessarily their own home or local neighborhood. In OSM, we often don't know where a mapper is actually mapping from, just where they're mapping. So here's a screenshot of a utility I built to show where a mapper was active in a given year, highlighting 5 different mappers active in the US in 2016. As we raise the threshold on the quantity of edits performed in each location as a percentage of a mapper's annual activity, we find that even mappers active all over the world, or in this case the country, typically have one area that they focus on far more than any other location. This is not to say that these contributors don't also participate in other forms of mapping, such as disaster mapping, just that many mappers have one geographic area that they give the most attention to. Edits performed by mappers in these localized regions are likely different from their edits performed in other parts of the world. Only contributor-centric analysis will let us investigate such a plan. A third community of mappers that has piqued attention lately is that of corporate editors. These are teams of editors employed by a company to edit the map, presumably editing features in relation to corporate interest. This map shows corporate edits made in OSM in the last 5 years. As you can see, it's a global phenomenon. These areas that glow white represent very high quantities of edits. Of most interest is how fast corporate editing has been growing, especially in the last year. Apple is now the largest corporate contributor by cumulative edit count, which has its own implications and makes some feel uneasy. What does this mean for an otherwise assumed entirely volunteer community of editors? I'll return to this phenomena in much further depth later in the talk, but for now, understand that without prioritizing the metadata that lets us ask who is editing, these types of investigations are impossible. And this is really the backbone of contributor-centric analysis. That was just 3 of the many types of contributors within OSM. Furthermore, there aren't rigid lines between these classifications of mappers. Mappers can choose to map for any number of reasons. More importantly, classifying mappers into specific categories is understanding the overall rate of growth. Today, there are about 5,000 mappers active each day on the platform, making millions of changes to the map. So that was an overview of the contributors behind the map. But what makes analyzing the OSM database so difficult itself? At its core, OSM is this database of geospatial objects. The screenshot of CU campus contains about 1,300 objects: roads, buildings, parking lots, cafes, bike racks, and more. The entire planet, again, includes 800 million objects. Each of these objects has their own editing history. While many objects are created once and not subsequently edited, over 238 million of those 800, about 30% of the map, has been edited at least once more. Each of these edits, however, does not correspond to a single entry in the database. So reconstructing exactly what happened is a bit convoluted. For example, given the OSM data model, there are many different ways that a mapper can change this object. This building, for example, is composed of 5 OSM elements, 4 node elements representing the corner points, and 1 way element that references the points and has attributes such as denoting its name and the fact that it's a building. There are 5 possible types of edits one can then make to an object in OSM. First, an object is created. In the case of a road or building, the primary element is a way, which then references a number of node elements that define the geometry, like we just saw with that building. A slight modification to the geometry, such as moving one of the nodes, will not increment the version of the primary element, but is rather reflected as a change only to the referenced elements. This is a very specific type of change that I will go into much greater detail later. Majorly modifying the geometry, such as adding or deleting a point, will affect both the primary element and the referenced elements. And editing the attributes of an object, such as adding a name or a speed limit to a road, it affects then only the primary element. And then last, a mapper can simply just delete an object entirely. So each of these edits means something different for the map. Adding a name attribute to a road or building could signify some level of local knowledge. Remote mapping, on the other hand, is often characterized by just these first two types of edits, as people are tracing satellite imagery and realigning and correcting objects on the map as they see fit. So here are two examples of what we're calling these minor versions, that edit type 2. We, in this case, refers to the small but growing number of OSM researchers that are trying to find ways to capture these changes. These red outlines show previous versions of the geometry of these buildings. The base map includes the most current versions. You can see the shapes and locations changing over time as editors are moving these corner nodes. I'd like to note here that identifying the complexities of minor versioning requires first building systems that can handle it and identify it, which really didn't come into being until just the last 2 years. I'm presenting this to you now in retrospect, but when I started this work, these minor versions fell into the category of I don't even know what it is I don't know yet. Additionally, there are edits that do not appear on the map, but are critically important to the data. This is a term restriction, just down the street. In OSM lingo, it's a relation element, a relation between two other elements, in this case, the object representing 28th Street frontage road and the object representing Colorado Avenue. The relation, then, is only right turn. We need to ensure that our analysis systems can capture edits to these types of invisible elements. Here are two cities with similar populations, about 3.5 million people. Rendered here are all of the buildings that are mapped in OSM. We see that Berlin is much more complete when it comes to building coverage than Lucknow, India. And we can do another comparison here between Yumbe, Uganda, and Casper, Wyoming. Also similar populations, the buildings are much more completely mapped in Yumbe. Geographic context matters when you quantify the map for analysis. The map means different things for people in different parts of the world, and assessment of quality attributes such as completeness are then very context dependent. Different regions of the map have distinctly different editing histories. Only by breaking down the map to the individual objects and edits can we really understand how the map evolved. Comparing the mapping history of the United States with Nepal, for example, will highlight two of these histories. These graphics show the number of daily edits here in blue, and then the number of daily editors in red. So for the US, an early massive road import filled in much of the map, and then before the community actually started to kind of grow. And then over time, we see a couple more building imports across various cities, and this kind of consistent growth of the community. In contrast, Nepal had a small but stable community of mappers, growing slowly over the last decade, and then the response to the 2015 earthquake blew everyone away with how much data was contributed in that immediate disaster mapping response, going from about 20 daily contributors to peaking around 1,300 contributors during the event. So everywhere really has its own story. To recap, each of these aspects of the database make OSM data analysis a multifaceted problem. It's big data, multiple types of edits with different implications. Where these edits occur mean very different things, and every part of the world has its own story. This is what contributor-centric analysis is designed to do. It allows us to reveal the data provenance to get at the evolution of both the map and the community behind it, addressing these complications in the data by prioritizing the metadata about the edit, tracking who made what changes, when, and where. And this requires embracing new analytical infrastructure. When I started this work, the dominant discourse around OSM was about data accuracy, completeness, and its ability to compete with authoritative geographic data sources. All the aspects you'd expect from a geospatial database and a map. However, what about areas of the world where OSM is the only map and there aren't other data sources to compare to? How about ways to understand not just how complete or good the data is, but how good the data will continue to be, how recent it is? Ways to understand how the community behind the map continues to grow and what the implications are for the map. Coming from HCI, not geography or GIS, I was predisposed to view OSM as a site of online collaboration. Being introduced to OSM analysis through disaster mapping, our initial questions were about how many people participated and how they collaborated. This meant incorporating data provenance. Each of these edits leaves a distinct signature in the database. By extracting these signatures to understand the origins of the data and the associated mapping behaviors, we can add more context to our questions. This is known as intrinsic data quality analysis, which I will return to in greater depth later. Contributor-centric analysis systems allow us to include these metadata that describe the data provenance in our geospatial analysis. These systems need to be extensible, allowing analysts to ask a range of questions about the data and its genesis, and they need to produce meaningful, interpretable output. And so this brings us to part two, the first contributor-centric OSM data analysis infrastructure that we built here at CU. This was known as Epic OSM, named after Project Epic. Built originally to support crisis informatics research, Epic OSM was designed to let users submit a set of analysis questions against a specific subset of OSM data. The NoSQL document-based storage model of MongoDB supports the open tagging schema of OSM. It preserved the OSM topology, storing objects as nodes, ways, and relations. And in support of crisis informatics research, the system was then optimized for distinct disaster mapping events, specific areas at specific times. Epic OSM was based on what we call an analysis window. These start with the spatiotemporal bounds, start and end dates, and a geographic bounding box. Next, the analyst would specify their questions, which were interpreted by the system and queried against the bounds of this analysis window. Here's an example of standard questions, but a primary advantage of creating Epic OSM in an interpreted language like Ruby meant that analysts could write custom question modules to be included at runtime. This allowed it to be extensible to any number of questions. With Ruby's support for metaprogramming, we designed Epic OSM to interpret and correctly execute human-readable question definitions, such as ways by day or change sets by hour. Epic OSM would read this analysis window, interpret the questions, and query a Mongo database that was pre-populated with the OSM historical data. The output of Epic OSM is then a directory of JSON files, one file per question. Some questions produce very simple output. Other questions that involve temporal binning, such as change sets by day, produce more complex files with this consistent binning schema, time bucket start, time bucket end, and the objects that fall within that window. These JSON files are then interpreted by OSM Down, a markdown rendering engine that produces static web pages. Here's an example of OSM Down page for the Haiti response, showing an interactive map in the center and a list of all the users responsible for the editing on the left. We built OSM Down to interpret and render a custom file format known as OSM Down files. This let researchers write up the results in standard markdown syntax and then include an OSM Down object, such as this map and timeline. When rendered, the static web page could be easily shared with other researchers. Clicking on the Show Code button would expand the code blocks that generated the interactive maps and figures to show others how the results were calculated, increasing the transparency and reproducibility in OSM data analysis between researchers. We successfully implemented Epic OSM to support 2 research papers. First, we compared the mapping practices between the 2010 Haiti earthquake and 2013 Typhoon Yolanda in the Philippines. This graphic shows edits by users, differentiated here by color. Haiti appears more chaotic, as mappers are mapping between and on top of one another. Typhoon Yolanda, on the other hand, shows a bit more blocky, segmented mapping activity. And this improvement in coordination between mappers is the result of the tasking manager, built by the humanitarian OpenStreetMap team, which allows mappers to alert others of where they are mapping at any given time. This graphic then visualized its successful implementation as a coordination tool for disaster mapping. Next, we used Epic OSM to extract specific types of editing patterns we identified in the Haiti earthquake response. To do this, we constructed interaction networks between mappers. With Epic OSM, this just meant writing a new question module for network questions. In this case, we built interaction networks among contributors in 2 ways. If their change sets are overlapping, they're mapping near each other, or if they're mapping 2 roads that are intersecting. Here are some of the visualizations of the collaboration patterns that we then identified in the data. This included finding one mapper who worked on roads while another mapped the buildings, and another mapper who added the side roads just to a main road that was created by an earlier mapper. So this research showed the ability of tools like Epic OSM to drive contributor interaction network and time series data analysis for large disaster mapping datasets. When the 7.8 magnitude earthquake occurred in Nepal on April 25th, 2015, I was actually in Chicago presenting Epic OSM at the annual meeting for the American Association of Geographers. We started ingesting the map data as thousands of contributors digitally converged to improve the map. We used OSM Down to produce this webpage with basic summary statistics of the activity. Epic OSM, however, had been designed for this historical analysis. We were consistently ingesting the data and recomputing the stats periodically. After 72 hours, however, there was just too much data being generated, and the analysis started to fall behind. This was especially nerve-wracking because hundreds of people were visiting this webpage in the days following the earthquake to track this response. By implementing a rolling analysis window, we were able to achieve something closer to real-time analysis, but the sheer amount of data produced during this event showed that analysis systems, especially for disaster mapping, were going to need to be able to scale better. So to review, Epic OSM met the goals of being an extensible analysis infrastructure that allowed researchers to write their own question modules to analyze a specific region of the map at a specific bounded time in history. The consistent structured JSON output was optimized for our OSM rendering engine, which allowed us to easily create shareable interactive visualizations. Unfortunately, however, the architecture's life was limited. It was optimized to handle disaster mapping events with hundreds of contributors. It was quickly becoming clear that disaster mapping activations were going to be attracting thousands of contributors in the future. And Epic OSM would not be scaling for analysis of these larger data sets. Vector tile-based analysis, this brings us to part 3, vector tiles. So vector tile-based analysis offered scalability and performance that Epic OSM could never achieve by starting from scratch, changing how we represent OSM data in the first place. Map tiles, shown here with red outlines, are a convenient way to represent spatial data at different levels of resolution. At higher zoom levels, the world is just cut into more tiles. Vector tiles are map tiles that contain vector data that is rendered by the client, as opposed to pre-rendered image tiles. There are many ways to get OSM data as vector tiles, but for contributor-centric analysis, we need to ensure that all of the metadata is included in these tiles. For this, we use OSM QA tiles. These are vector tiles containing all OSM data that can be converted to GeoJSON, including the most recent editing metadata. OSM QA tiles are made available daily by Mapbox as a service to the OSM analysis community. The dissertation goes into much greater detail about the analytical benefits of GeoJSON and the production of these QA tiles, but I'm just going to skip that for sake of time. So this is what's inside the OSM QA tile that includes Boulder. Here we're looking at about 39,000 different objects, and we can count the number of distinct editors from the metadata and see that there's about 457 mappers active in this area producing this data. And this is just one tile. The populated landmass of the Earth is comprised of over 2 million tiles. OSM QA tiles were optimized to work with tile reduce, an open source map reduce framework built for efficient parallelized processing of vector tiles. Initially designed by Mapbox for fast quality assurance analysis of spatial attribute completeness, it can be easily extended to support our contributor-centric questions by incorporating that editing metadata. For an example, let's consider this map here of Boston and these 3 questions. How many contributors have been active here? How many buildings have they edited? And how many kilometers of road? Tile reduce then distributes tiles to however many processors one has to give it, running our custom map function against each tile in parallel. In this case, we have to write 3 analysis functions, one to count the users, the roads, and the buildings present in the features on each of these tiles. The map function returns any value to the reduce function for a map reduce architecture, but I found a more effective tile-based analysis workflow is to just output the results to a line-limited file for further analysis. Similar to Epic OSM, these output files then contain any number of summary stats, but instead of being temporally binned, they're spatially binned by tile. In this case, the quad key of the tile is used as our spatial index. This entire workflow allows us to ask questions like these of the entire planet in just a few minutes on a pretty modest machine in the cloud. Our output files contain over 2 million tile summaries, a manageable data set for standard data science utilities like Python or R. So let's go back to this rendering of object density I've been showing to illustrate the scale of OSM. These densities were computed using exactly this workflow. Simply go through and count the number of features present on each tile. Since we're only quantifying the data here, the map data, I consider this to be a data-centric view of OSM. But we can go one step further to incorporate the metadata to be more contributor-centric. So here's another rendering of object density, from white to red here on this log 10 scale. However, we're only showing tiles where more than 10 mappers have been active in the last 18 months. We shouldn't be too surprised at where this editing is happening. Europe is very dense. Many major global cities pop out. We also see some parts of sub-Saharan Africa and Southeastern Asia where many mappers have been active recently, both localized communities and remote humanitarian mapping. This is 91% of all the mapped objects in OSM. So it can really be summarized simply as where there are many mappers actively editing is where nearly all of the map is being edited. But now let's look at the other side of that, where 10 mappers or fewer have been active in the last 18 months. This is exclusive of that previous map, meaning that none of these dots represent the same tiles on that previous slide. While there are far fewer contributors in this map, and generally less red areas, meaning less object density, there is activity all over the globe. We see that it's certainly uneven, but it is happening pretty much everywhere. This contributor-centric view of the map tells a more descriptive story than the initial object density rendering. It's a big world, there's a lot left to map, but it's happening. People are active everywhere, and the entire world is slowly being mapped. And from a technical standpoint, it's again important to note that tile-based analysis like this takes at max about 10 minutes to run for the whole planet, which solves the constraint of making this a very scalable workflow. So there are two primary limitations of OSM-QA tiles, however, that analysts need to be aware of. First, because these tiles contain GeoJSON representations of the objects, only geographic map elements can be represented. So there's no support for relations, most relations. Most importantly, this means we can't count edits associated with things like term restrictions. Term restrictions are complex objects, and their presence has huge implications for knowing if the map data is complete enough to be used for things like routing. To address this, I created what I call OSM-QA Tiles Plus. These are OSM-QA tiles that are enriched with term restriction features. Since the actual shape or geometry of a term restriction is abstract, I simply represent it as a point, generally where this restriction applies to the map. In this way, I ensure the metadata associated with this edit is included in this tile. They show up here marked as term restrictions with the appropriate metadata. This allows us to quantify these objects and know when they were edited and by whom. Here we see a map of the term restrictions in Panama City. There's over 1 million term restrictions in total around the world. Second, OSM-QA tiles only contain the most recent version of an object. On the right here, we see the object representing Boulder Creek. This object shows that the original OSM layout element is in its 9th iteration. And we have metadata for this 9th version. We don't know anything about the previous 8 versions, especially not who created them and when. To this end, OSM-QA tiles are effective data sets for letting us analyze the current state of the map, especially in a contributor-centric manner with this inclusion of metadata. But can we use OSM-QA tiles to explore the evolution and growth of the map over time? And this brings us to part 4, where I'll show how we use historical snapshots in this OSM-QA tile format to perform historical analysis. So historical snapshots are OSM-QA tiles that capture the entire map as it looked at the end of each year. These were originally made available going back as far as January 1st, 2006. These tile sets allow us to compare what the map looked like at annual intervals. On the right here, we see what the data was available in London in 2007, only that bright green data, and then we can see what London looks like today in terms of map coverage. The work described here was part of a 2016 summer research fellowship with Mapbox, where I was first introduced to OSM-QA tiles in these historic snapshots. And then this is what it looks like to extend the tile reader's workflow to handle annual snapshots. We write single tile radius analysis jobs and run it against each year. Here I'm only showing 7 years, but you get the idea. For each year, the script filters for edits that happened during that year, meaning since the previous snapshot, and this ensures we're only considering the most relevant metadata. Output then remains per tile resolution, but can further be broken down by user or date for more descriptive results. These output files may contain spatial information that can be turned back into vector tiles to drive interactive maps, or text files which can be easily ingested by Postgres to allow us to write SQL queries against OSM metadata history. Let's see an example of what these databases can do. So let's take the question, how many new buildings were added in Haiti the week after the earthquake? This question can be turned into the following query. We calculate the number of new buildings per tile and group them by day and save them to the table of 2010 edits when we ran that map reduce job. The region on the right shows the zoom level 8 tile covering our area of interest. Using the quad key spatial index here, we can easily limit our search to the 256 OSM-QA tiles that are included in that area. And we can now find that there's over 6,000 buildings added to the map in that first week after the earthquake. Using this approach, I calculated a number of statistics about the editing in the United States. These were presented at the 2016 State of the Map US conference. Here we see the total number of users active across various US cities. Generally, we see a healthy, growing community in each of these major cities. We could break this down by buildings. We can see the number of buildings on the map as each city grew. Each of these big steps represents an import effort, typically done by a local mapping community. We can also look at the changes to density of edits in the US over time, showing us how the map filled in. However, where things get more interesting is if we go one step further and break down this editing activity per contributor to be more contributor-centric. This lets us revisit this investigation and interaction networks among contributors. Here we see co-editing networks in 2010 for contributors who mapped at least 25 kilometers of road on the same tiles. And if we highlight this cluster here, we see this is mapping that happened in Haiti, presumably right after the earthquake. We can also explore where these contributors mapped that year and see that many of these first disaster mappers were from the German community. When the earthquake struck in Haiti, they then shifted their mapping focus to mapping Haiti. Here's one more utility I built to explore the distinct editing histories computed per country from the annual OSM QA tile snapshots. As we click through various countries here, you can see each one has a very different history in terms of how fast the number of daily contributors increases over time. These visualization tools allow us to compare the intrinsic attributes of the map, including the growth of roads, buildings, and the number of contributors active over time. So when looking to investigate the quality of the map, intrinsic measures, again, rely only on the attributes present in the data. This is distinctly different from extrinsic data quality analysis, where we compare OSM to other more authoritative data sources. Intrinsic analysis is then the only feasible approach to data quality assessment when OSM is the only source of geospatial data. As we saw, disaster mapping has a profound impact on the amount of data added to the map. This journal article then investigated the implications for intrinsic quality analysis. Most importantly, for these areas, OSM is the primary source of geospatial information, so extrinsic data quality analysis is just not possible. We explored these implications on 3 metrics: density of contributors, experience of contributors, and the types of editing that was happening on these tiles. The 4 study areas were Port-au-Prince, Haiti, Tacloban, Philippines, Monrovia, Liberia, an area that received a lot of mapping attention during the 2014 Ebola outbreak, and Trezuli Bazar, Nepal, an area that was heavily affected by the 2015 earthquake. In one of the first OSM quality analysis papers, Hackler et al. Identified that once the number of mappers active in a square kilometer surpassed 15, the quality of OSM, when compared with other authoritative sources, was very good. To compare, we calculated the users per square kilometer from these annual snapshots, and the yellow bar here represents the year where the disaster mapping occurred. And this red line represents this quality indicator of 15 mappers per square kilometer. For comparison, we also calculated these for Heidelberg, Germany, and London, UK, areas known to be of high quality through other investigations. We see that Heidelberg and London, these areas reach this threshold of 15 mappers very linearly with this just sustained growth. On our 4 subtiles, however, we see that disaster mapping causes a major jump in this pattern, most likely bringing in non-local contributors or perhaps less familiar or inexperienced mappers who are instructed to map specific objects. Next, we compare this to the general number of contributors active each year. Again, Heidelberg and London show a sustained increase in annual contributors and then appear to level off more recently. Contributors here are considered experienced if they've been active on the platform for more than 7 days. In contrast, we see that the year with disaster mapping brings the most contributors to each of these tiles, interrupting this kind of sustained growth pattern. And again, the year here is highlighted in red. The Nepal earthquake also saw a much higher percentage of new mappers contributing to the event. Our final metric looks at the evolution of the map. This metric is based on a previously observed pattern of mapping evolution in OSM. First, the node network fills in, the road network fills in. Next, mappers add new buildings. And then once the map is kind of filled in, users are primarily then only editing the existing data. So this last behavior has been coined map gardening by Alan McConchie, based on similar maintenance behaviors seen on wikis. These bars represent these types of edits as a percentage per year. So in London and Heidelberg, we do see this kind of overall pattern emerge. First, the majority of mapping activity is new roads with a bit of editing to existing roads. Then in 2009, 2010, we see a lot more new buildings coming in. And in more recent years, fewer new roads, relatively fewer buildings, and a lot more editing to the existing roads and buildings. In contrast, the disaster mapping events, again marked in red on the x-axis, appear to accelerate or interrupt this pattern of growth, as mappers are explicitly instructed on what to map. Ultimately, disaster mapping leaves a distinctly different editing signature in the data that data quality analysis, especially intrinsic quality metrics, need to be aware of and know how to identify. Data quality is also entirely relative. These areas may be of different overall quality with regards to meter level accuracy found in some parts of the world, but these data were contributed and used for safety and time-critical disaster response and relief efforts. This means an entirely different context for analysis of quality. One analytical weakness here is the resolution of analysis. Annual snapshots can only provide annual resolution to investigate these questions, meaning only one edit per object per year. Because the snapshot is created at the very end of the year, it only captures the latest edit in the year. While the version number tells us if it's been edited before, we don't know any information about those previous edits if more than one has occurred during that year. I call these edits shadowed edits because they are being hidden by the edit closer to December 31st. I developed a formula based on the version numbers of objects found in each year to visualize the total number of shadowed edits occurring around the globe. Early on, it's not too bad, but in more recent years, many edits are going shadow. As part of a 2017 research fellowship with Mapbox, I set about improving snapshot analysis resolution by creating quarterly snapshots. These capture what the map looked like on March 31st, June 30th, September 30th, and December 31st of each year. This is a screenshot of the download page where anyone can go download these quarterly snapshots for their own analysis. These quarterly snapshots give us 4 times better resolution at only 4 times the processing time. Because quarters are a familiar temporal unit for reporting growth and change over time, this increase in resolution at the expense of processing time seemed a fair trade-off. To get a better idea of what's going missing in these annual snapshots, we can count the number of edits per day between the two and compare. The difference between the 2 lines then represents the number of shadowed edits per year. And here we can see that there are certainly a number of edits being shadowed by these annual snapshots, about 8 million per year on average that we can identify with our quarterly snapshots. Using quarterly snapshots in North America, I collaborated with Mapbox to build the OSM analysis dashboard, which I presented at State of the Map US 2017. Here you can see a comparison of the number of mappers active in the last quarter of 2009 and the first quarter of 2010 when the earthquake occurred. This dashboard also further improved the scale of analysis by moving the zoom level 15 from 12, giving us 64 times more detail. Here we see the density of buildings in Los Angeles, California, before and after their building report. One more example shows the increase in total mappers active across North America between 2012 and 2017. Quarterly snapshots over annual snapshots here allow us to ensure those editors active early in the year are being accounted for. And most recently, we used quarterly snapshots to investigate the growing phenomenon of corporate editing in OSM. Best practice, as instructed by a set of community-defined guidelines for anyone involved in organized editing, such as corporate editing, is to maintain a list of usernames associated with their editing activity. Contributor-centric analysis lets me identify these companies based on these lists of usernames and see their editing footprint. As you can see, this activity is global for some companies such as Mapbox, Apple, and Cart, primarily focused in North America for companies like Amazon and Telenav, and then more localized for companies like Grab, Uber, and Facebook. Next, we can compare the type of mapping corporate editors are doing with other mappers active on each of these tiles. The takeaways here are that where corporate editors are active, they are, on average, responsible for the edits to the majority of the editing to the road networks. Non-corporate editors, however, are still the dominant mappers of buildings and points of interest in these areas. Corporate editing also leaves a very distinct temporal signature in the database. We see a 5-day work week appear. Each of these groups represent 5 days of editing activity, punctuated by 2 days off. This is a telltale sign of paid editing, where editors are only active on weekdays when they're at work. We see this pattern among other mappers in the database, and future work will investigate whether these are from undisclosed paid editors. In summary, this journal article shows that corporate editing represents just the latest stage of corporate involvement in OSM. By tracing the history of corporations in OSM, we showed that corporations have been a part of this community for more than a decade. The donation of satellite imagery, for one, enabled remote mapping in the first place. While corporate editing is a growing phenomenon, it's not going unchecked. The community is actively keeping tabs on it, and the 10 corporations that we investigated here are currently adhering to these organized editing guidelines. And so far, when issues have arisen, they have been, for the most part, resolved between the community and the corporations. So bluntly put, this is not currently a corporate takeover, but it does prompt the need for further investigation and monitoring. This work only showed the footprint and the type of activity, which begs the next question of, what does the interaction look like with other mappers in the area? This is really just the tip of the iceberg. To understand the impact of what corporate editing looks like, we need to break down the map to the individual object histories in each of these areas to compare, to see exactly what the interaction is. To do this, we need to go past snapshots to show what the map looked like at any given time, and interrogate the full history of an object, how it changed, when, and by whom. So this brings us to our final part, tile-based analysis with full history of OSM objects. To uncover the actions between edits, we need new data schemas that can capture the history of an object, representing the changes between each version. Here's an example of what this looks like for Folsom Field across the street. You can see when it was created in 2013, it was given the tag Sport, American Football, Leisure, Pitch. A couple months later, the name tag Folsom Field was added, and then 2 years after that, we see someone denoted the surface as grass. Recall the problem of the minor version. Our history schema needs to recognize these. When an object is first created, it's assigned a minor version of 0. When the geometry is edited, the minor version attribute is incremented with the metadata for that change. We also record when that particular geometry was present and valid on the tile, with valid since and valid until timestamps. So why do minor versions matter so much? First, they're not recorded in the primary OSM element, so they require novel systems to calculate. Second, they represent a very specific type of edit, a validation or a correction of the object on the map. Knowing that minor versions exist then offers this sense of implicit validation to the map and the objects around it. So for example, if a mapper comes in and corrects 4 out of 10 buildings by creating minor versions, we have this implicit validation that the other 6 buildings are also correct. Otherwise, they probably would have edited those as well. There's 96 million objects in OSM, that have at least one minor version to them. The total number of minor versions on the map then is 211 million. And these minor versions are the cumulative work of over 400,000 mappers. So it's really important that we're able to count these edits to give credit to these contributors. There are 2 ways to record and represent an object's history. First, we can embed the history in the object itself as a specific history attribute, as I showed with Folsom Field. In this way, we know both where the object currently is, and we can query the history attributes for the historical versions. This is optimized for tile-based analysis, where an object's history is exposed to the map script, which operates then on each tile. This allows us to calculate questions like which users added names to the objects in this area. Or as shown here, how has the geometry changed over time? This graphic shows the current outline of this building on the left, and the previous 9 versions, 3 of which were major versions, and 6 of which of these were minor versions of this object. Second, each individual historical version of an object can be represented as its own object, tracking when it was visible with those valid since and valid until timestamps. This is optimized then for interactive visualization, allowing us to render the map as it existed at any point in time and have access to the object's metadata at that point. This is a screenshot of data in this schema being represented on Kepler-GL, a visualization platform built by Uber. So how do we compute an object's history and build a full history of vector tiles? Originally started in collaboration with Mapbox, OSM Wayback is a utility to convert an OSM history file into history-enriched GeoJSON objects that I've been building over the past 2 years. Here's a screenshot of OSM Wayback processing the historical data for Port au Prince, Haiti. In OSM Elements, this is about 3 million nodes and 600,000 ways. This translates to about 270,000 current OSM objects with over 600,000 previous versions of these objects that we want to capture. And it takes just under 2 minutes to process all of these histories on this laptop. Again, scale that Epic OSM could have never achieved. The dissertation goes into much greater detail about the architecture of this utility. I'm happy to take more questions on that after. So here's the result. As we zoom in, we see all of the buildings in Port au Prince. Embedded in each of these objects is then its full editing history. Since GeoJSON flattens the topology of the original OSM object, we lose the efficiencies of the node-way data structure. Since multiple versions of an object likely have similar or the same geometries, there will be a lot of duplication if we store every one of these geometries. TopoJSON allows us to topologically encode our history objects and convert them back and forth to GeoJSON seamlessly. This limits the duplication of data, averaging about a savings of about 25% in file size, depending on the area. So currently there are 2 other systems capable of calculating OSM object histories at scale. First, OS Mesa leverages Apache Spark for scalable batch analysis of historical OSM data, capable of computing minor versions and retaining relevant metadata. The process histories are stored on Amazon, which makes it easy to query with Amazon Athena. Many of the summary stats presented here were computed this way. This animation, for example, shows Athena scanning 28 gigabytes of OSM history data in just 22 seconds to calculate all those stats on the minor versions I just presented. At the 2018 State of the Map US conference in Detroit, Seth Fitzsimmons, a core maintainer of OS Mesa, and I ran a workshop on OSM data analysis. Our goal is to take the data wrangling out of OSM analysis and let participants jump right into the data. We provided pre-processed data from OSM Wayback and OS Mesa that included the full editing histories for over 40 different US cities. We provided sample analysis notebooks that let participants get up and running immediately with questions about the evolution of the map and their local editing communities. This included questions like who were the top mappers in the area, and then in this example, you could create an interactive heat map of all the buildings edited. And so here's what that looks like for Detroit. So yeah, this let participants in the workshop completely skip dealing with OSM data and jump right into this analysis. Second is the OSM History Database, an awesome project from the Heidelberg Institute for Geoinformation Technologies. These latter two systems are capable of handling minor versions and all OSM elements, including relations. I bring these up not just as related research, but as planned future collaborations. Historical OSM research isn't happening in a vacuum. The maintainers of these other systems and I have been continually in contact as we develop these infrastructures in parallel over the years, working through our various complications and coining terms like minor versions. The future of my work includes planned collaborations with these two other systems to better improve and provide full historical tile-based analysis opportunities for all OSM researchers. With few exceptions to this ongoing work, what I just presented to you is how far I've come with the development of contributor-centric approaches to OpenStreetMap historical analysis. Here's an overview of the research I will be conducting this coming year to continue pushing the possibility of OSM analysis. And I close with this goal of contributor-centric approaches moving forward, to continue closing this gap between the questions that we want to be able to ask of the data and the questions that we actually can. So with that, I'd like to thank my committee, my friends and colleagues in Project EPIC, external collaborators and colleagues, Mapbox and my collaborators there, as well as the various OSM groups that I've been associated with over the past 5 years. This work has been funded by the National Science Foundation, Mapbox, and received computational support from the Chameleon Testbed for Computer Science Research. Thank you.
Okay, thank you, Jennings. All right, so Zhao, can you hear me?
Yes, I can hear you.
Felicia?
Okay, great. So what we'll now do is open up questions from the committee members. Zhao, would you like to begin?
Yes, thank you very much. I will begin. I'll just ask to try and switch on my video so that you could see me. So just give me a second. I will try to switch on and then I can begin. So.
Can you see me? I just turned on my video. Oh, there you are. Okay, perfect.
Oh, yes. Okay, so you can see me now. Okay. So hello. So thanks for the talk, Jennings, and for the invitation. It's been a pleasure to read your PhD thesis and hear your talk about it. I have a couple of questions here grouped in 3 blocks. So they will be mostly around your research questions and contributions and some insights from the analysis. So start with the question itself, the research question itself. So I think like you described it quite well, the different types of challenges and analytical challenges that you addressed. So I was wondering, since you didn't have it fully articulated, what would you see as your main research question that you're tackling?
Yeah, okay, that is a great question. This is something I was trying to figure out along the way here in the last 6 years. And I really see two points here. The first is coming up with what's the framework we need to be able to ask the questions that we want to. And that's where kind of contributor-centric analysis comes in, and saying that our questions need to embrace this, our questions of OSM need to embrace the data provenance, include the metadata to provide more context. That's what separates OSM data from other general geospatial data, right? We have these extra editing attributes. We know when and who contributed this. So that's kind of taking that HCI sensibility towards the data of saying this is about the people behind the data as well as the data itself. So first, it's framing the question in that way. And then I think the contribution specifically of this work is to say, okay, first we identify that that's how we need to frame the questions. But then we need to start from the ground up, all the way from the bottom of the stack to create these systems that can enable this analysis. And a lot of this is extending existing systems, small modifications, putting different existing systems together, and writing a lot of things from scratch. So that's what I see as kind of the technical contribution to this work, is providing the framework for infrastructure for people to ask questions framed in this way. But where it gets complicated is that the first thing you have to do is kind of take your question and then revisit it from the contributor-centric perspective. And so for example, like with the minor versions, like that's an example of a question that we didn't even know we needed to be asking until we looked at the data in that other way and incorporated that metadata and realized that, okay, sure, it's interesting that these things are changing in multiple, there's all different ways people can edit it, but more importantly, there's 2 or 3 more editors that are part of the history of this object, and that really means something other than just how did this building move. It's knowing that actually there wasn't just 7 people that contributed to the history here. There was really 10 people that were actively editing this object.
Okay, so I think when addressing this, you already moved into the contribution. So I think maybe we can continue with this. So when you say you try to articulate how to ask questions about the OSM data, these are related to your own research questions. That's interesting to see. What would be interesting maybe to spell out in terms of the subcomponents of your research contributions? What do you think that, for example, that these need to ask questions around the who in OSM? How does that translate into the scientific challenges you are addressing, and then the contributions you are making, adding to the to the bodies of work, state of the art in specific areas that you would be tackling? So maybe you can just give an overview about these challenges and your contributions towards that challenge.
Certainly. So where contributor-centric analysis, the need for it, really clicked for me and kind of hit me over the head pretty obviously, it was probably last fall when I started investigating this question of corporate editing. And there's many ways we can analyze spatial data. That's a whole field of science itself. But having this infrastructure in place, we were then able to say, wait a minute, this isn't about what the edit is or how complete the map is. This is about who is editing. And being able to quantify and study that required these approaches. And at the time, I had this infrastructure set up and I was able to ask these questions and start to uncover what this looked like. And suddenly it was the most important part of that data and that study is being able to ask who. And so, and I think this has huge implications for the community moving forward. This is a big area of my planned future research, is then further investigating this interaction with corporate editors and non-corporate editors. So I see that as kind of another contribution to the questions that we can really begin to ask. And again, this isn't about the quality of the spatial data. This is about the interaction between the contributors on this online platform to study that underlying interaction to see how this is affecting the map.
Yeah, I mean, so maybe what I'm trying to get really here too is, thinking about, let's say, existing approaches, let's say, to support this spatial temporal analysis of geospatial data, in terms of the specific challenges you've had to address. So I understand they are in part connected to the idiosyncrasies of the OSM database and data model, right? But what will be interesting to hear is really because you are developing a new method here, an analytical framework, an analytical method, isn't it? So I think what I'm trying to understand, is how you see this in the context of other approaches to, let's say, spatial temporal data science or other frameworks and methods of analysis of spatial temporal data.
I see it as a combination, right? More an extension, I think, thereof, like extending what we can do with things like intrinsic data quality analysis. We have a set of known, quality analysis for geospatial data, attribute, completeness, accuracy, and those are all typically studied with extrinsic data quality analysis, comparing those to other data sets. There are no limits for what we can do with intrinsic analysis. We can just come up with more methods and indicators from the data. And what separates OSM data then is these extra attributes that we can combine in any number of ways to get at kind of further measures. Another complication I'll add on that is then not just who or how many, but if we now know more information about the contributors behind it and the interactions behind that, we have a sense of, for example, corporate editing or paid mappers that we know have specific validation practices in place. That offers, if we know that editor was active in an area and we know there's oversight and strong management from that editing team, that has an extraordinarily different implications for things like existing kind of quality analysis that we don't have access to in other methods. And so that's where I see the power of this is just embracing all the different ways we can combine the metadata and what we can tease out of the metadata there. So in many ways, I see this as kind of a lot of this is an extension of other investigations into this, right? Like there have been a lot of other investigations of intrinsic quality analysis, looking mostly at recency, number of contributors, et cetera. But by breaking it down at the per edit level, we can start to look at not just how many contributors, but really who and experience and what that can mean, for the map. And so that's kind of how I see it comparing to kind of other methods of geospatial spatial temporal analysis.
Okay, great, thank you. I think just a quick add-on to that before I move to my last couple of questions about the insights of the analysis. I notice actually that it maybe implicitly, but you are doing your analysis in a global level, right?
Yes.
And that's actually what generates your kind of specific challenge of addressing this at scale, isn't it? So I was wondering that because you don't really discuss this need to do it globally, so why don't you do why the requirements for this global level, where do they come from? Or how do you think, or to what extent they are important for your work and then, give you requirements that are associated with this, spatial and temporal scales?
Certainly. So initially, and that's what set us down, this first path was, and honestly, depending on the questions you're asking, global analysis doesn't make a lot of sense for many questions because you can't compare the whole world with itself, right? This is very geographically context dependent. That's from a kind of spatial data quality perspective. However, what we quickly learned, so the first analysis we compared, Haiti with the Philippines and then Nepal, and certainly the data was growing too big, we didn't need to go all the way to the global scale. But now, if you just want to ask a question about how many humanitarian OpenStreetMap team associated edits were made yesterday, that's a global scale question. There's activity happening all over the world every day. And so when we ask these contributor-centric questions, if we're asking about kind of the map as a whole, as a community as a whole, there are people active everywhere, every day. And that's what kind of drives the need. Once I found these approaches that could scale with the QA tiles and this tile-based analysis, it was really hard to wanting to go back because suddenly, things are popping up in I love when I run these analyses, it's like there's an area of the map that I didn't even expect there to be edits there for that event, and you can drill down on that, and there's some reason that people are editing there. And so I see, when we're considering all the contributors, we're considering what the community is, it really is globally active, and I think that that's important to capture in a lot of these systems. While we can't compare the map per se, one place to another perfectly, we can get a better idea of this, of how much global activity is happening.
Okay, great. Yeah, that sounds interesting. I think related to this, still in terms of the scales of analysis, you know, as a geographer, I'm particularly interested in this, and I was actually, I thought you mentioned this in the thesis, you know, by passing about the influence of actually the tiles, you know, or you know, I think there is a discussion about really the objects that are in between tiles, right, or that cut across different tiles. And I think this is resonates, you know, a kind of like long-standing problem in spatial analysis, which is really the size and shape of spatial units, which is so-called modifiable area unit problem. And interestingly, I think your work addressed you know, dealt with this in a way, but you didn't kind of like explicitly. You know, I was wanting to get your thoughts on what is the influence of the size of the unit, let's say the zoom level, which is for you actually give you the spatial unit in the analysis, and how do you think is the best way to tackle this?
So yeah, exactly. And there's a lot of things that I kind of glossed over in the presentation, certainly that I go into a lot more detail. First thing is that a lot of what I presented here, that was we're all using zoom level 12 tiles as a base unit of analysis, which has its own problems because given the way the world's cut up with the Web Mercator projection there, these tiles do represent slightly different sizes depending on the latitude. So a more accurate approach would be to normalize by square kilometer, normalize by area of the tiles. However, I do know when you do that, all these visualizations look exactly the same. So I can show that after. So that said, though, the features that actually can get represented in the tiles, and how features are split across tiles, and the problems that creates, these are all just the nuances of the complications of OSM data and how we can represent it. And I have kind of a whole list of these problems, of these tiles that don't make them unusable, but certainly analysts need to know why they're getting the results they are, and know how these nuances are affecting their results. I like just trying to be as accurate as possible. I settled on zoom level 15 because in many parts of the world it represents about a square kilometer, and that's a kind of a standard unit of analysis. And so I think that makes it easier to communicate these results. Like zoom level 12 is kind of an odd unit to try to convey. It's about the area of a small city, but it does have variations across the globe. So I think zoom level 15, the more tiles we go into, it becomes unmanageable to represent the whole world. But I do think that zoom level 15 is just a kind of a little bit of a cleaner, simpler analysis. And when you get to a city level, it really lets you break that down. And it's a couple of blocks of what editing is happening. And so seeing if you could tease out like more local neighborhood editing kind of happening within that interaction. But it is, it's just the way that OSM data is then represented and how it's tiled leads to a whole number of complexities. And I just kind of always have a big list of those issues. So it's something that people need to be aware of. I don't think it invalidates them as an approach, but just something that we certainly need to have a lot of caveats that people understand what they're looking at.
So what I was actually asking for, when they would discuss it, the influence of temporal units, because in your thesis you went down to smaller and smaller temporal units, isn't it? Then up to being very granular. you explore the kind of like shaded edits, which actually are a problem of the aggregation. You know, in spatial, when we talk about spatial, we have something called ecological fallacies, which is similar, kind of like context. In a way, I was actually wanted to hear your thoughts. Really, what do you think are the influences of this kind of like scale of aggregation spatially, and the size of units in the different processes? What you call like the nuances of the different processes for generating this peer-produced spatial information, you know, because I think that's your phenomena, isn't it? In a way, in like that, what do you think it's the characteristics that might be masked or might be, influenced by size, and by geographic unit here when you're looking at your analytical needs, which are really targeted at, revealing these different processes?
Yeah. So I'll kind of answer that kind of with linearly and how I kind of observed this. At first, I thought that the annual resolution was fantastic, and I started working with those in 2016. And for many parts of the world we're looking at, it was fine up to about 2012. And was doing all this quantification, finding all these edits, looking at how things changing over time, we're able to kind of see these general patterns. The problem came then when I started to look at cities. And aggregated that, well, for the temporal bounds, the spatial bounds don't matter there, but starting to look at these edits across cities and starting to count how many edits were going missing. And it was like tens of thousands of edits were going completely hidden. And things were jumping from version 3 to version 10. And that's a lot of information to not have access to. That's potentially 7 contributors that are not being counted in the history of that city. I didn't show it here, but I have kind of another interactive version counting, only users active presently versus all users computed from history. That's what made us take the jump to quarterly. I thought about for a while if we just used all the daily snapshots and kept all the daily QA tile, that would be the most accurate, but that's just computationally infeasible. Each of those files right now is about 80 gigs. So having that on a single machine or an analysis just doesn't make sense. So that's where we settled on quarterly was, we found 8 million more edits each year. But still we're going to have masked edits, shadowed edits. And that's where I kind of abandoned that thread of these snapshots and said, no, we need a better way to represent these objects in full, because we need to have that temporal resolution down to the second for all of these objects. And so that's why I took that approach, because there is no scale snapshot that's going to capture that activity. And that's kind of why I made that jump. But I think that's just a very important piece of this work, is like, we can talk about quantifying the contributors, but we're doing it not 100% accurately if we're not incorporating that full history. So we can certainly learn something, but we can always learn more. So that's what makes me really care about that temporal unit.
Okay. Yeah. Right. Yeah. So actually, the question was related to extrapolating from the temporal to the spatial. Do you see like similar problems with like the geographic units that you saw in the temporal, or do you think the issues would be then different in terms of aggregating spatially instead of aggregating temporal?
Sure. So actually, no. What's most convenient about the organization of the data in this way is that all of the objects are getting rendered. We're not hiding any level of objects depending on the size of the tile. The tiles just get bigger. So they're not, they can't serve them over the web, but all of the data with pretty much unsimplified geometries are being represented at either 12 or 15, so the tiles are just bigger or smaller. And so there's trade-offs depending on how complex your questions are, to how big tiles should be, just in terms of the size of the tiles. But the data itself, that's what makes these powerful tools for analysis, is that the data itself is all being represented at any of those zoom levels, which I think is the main benefit of this approach.
Okay, yeah. So my last question would be about this. It comes back to the question of your contributions, but thinking about really thinking about this as a general, like or the type of general qualities of the contribution you're making, right? So I think you described it that your analytical needs as the need to capture these nuances and the processes that generated the data, isn't it? And in a way, this idea of the communities within the community, and actually you've shown to us some examples, right? And then could you maybe elaborate a little bit further? What do you think it's the general approach here, or the general vision of of how your work could contribute to this, to reveal these different communities in the communities, or different processes, or different, what's the roadmap for this type of understanding the different processes that generate the crowdsourced or citizen-generated data?
Yeah. So.
If I could interrupt too, this might have to be the last question.
Okay.
Let's maybe, Zhao, sorry, I'm going to ask Jennings to answer this question briefly so we can move on to the questions of the other committee, if that's okay.
Yes.
That's an important question.
Sorry about that, later. It's really my last one, and
no,
it's
okay.
very quick answer should be
yeah,
totally
it's an
fine.
important question, but Jennings, maybe you can do that. We can segue into the next question.
Yeah, absolutely. So what I was going to go with that is it's been a really fun time in OSM kind of analysis, especially the last couple of years, as these infrastructures are only now just coming about to access to look at these questions. This has been supported by the development of the big data technologies to allow us to do this and look into this. And for example, again, the enlightening part for me was part of the corporate editing was saying that now that we have these approaches where we can start to get at this behavior, and we can start to identify these types of communities. And when we first mapped that, it was like, oh my God, there's a lot more happening on the map than we thought there was. And that was just exposing, one type of community. And so I see this is really, I do consider this just the tip of the iceberg with the development of being able to identify what's actually happening in the map. I think that we now have ways to quantify this activity through approaches we've never had before. And it's all kind of happening in parallel. I mean, the OSHDB, that paper came out like 2 months ago, 2-3 months ago, and that's now in active implementation. So yeah, moving forward, as we kind of combine all these pieces, we now have the tools to even know that these are the questions that we want to ask. And that's going to require a lot of iteration on how to get at kind of deeper, bigger questions behind that. But before this year, I couldn't have even answered a question about the corporate editing at a global scale. And I don't think very few people could. And so that's kind of where I see this again. Like the contribution is now moving forward. What questions have we opened up? What type of analysis can we now do? And now let's try to identify more of these communities in the data, and we'll just be excited to see what pops out. I mean, 5,000 active contributors editing daily, making 1 million changes to the map daily. So I think there's just a lot of activity that we are now able to quantify and view that we haven't been able to get at before.
Thank you, Zhao.
Thank you.
Jennings, yeah.
Thank you.
Who on the committee would like to next ask a
I can go
question?
next. So segue to what you said about 5,000 contributors. So you've done a fantastic job building this infrastructure to understand what have been doing, taking the contributor-centric approach. So I'm interested in the particular direction of future implication would be like the feedback loop back to those contributors. If there's a way, what does it take? I wonder if you can sketch. What does it take to provide some of the recommendation or real-time suggestions where they should go to contribute? If there's a way to assign utility to a particular edit, how can you tell the contributor, hey, this is where you should go? They could maximize the marginal benefit of the edits.
Certainly. And what's great is that like the project is already at a large enough scale that there are many different things implemented to do that. Probably the largest platform for that is going to be the task manager from the humanitarian OpenStreetMap team. Well, currently, I don't know what that number looks like right now. Tens of thousands of contributors actively participating in those tasks, directing users of where, from a humanitarian standpoint, like where it needs to be mapped. And then there's also
that is like by a human, or is the directions actually?
Those are all generated by humans. Those tasks are all generated by humans. So then on the other side of that, there are a lot of tools out there that are constantly monitoring the map, doing comparisons to like address databases, for example. So the OSM inspector is a tool that's out there so as we've been doing like the Denver building report, for example, the OSM inspector will come up and flag things that it thinks are suspicious in terms of data coverage and accuracy. And people will then go in and they can use that as a way to kind of automatically identify areas of the map that need focus. And that allows people to kind of look at specific areas. So if I really care about the map in Denver, I can run the OSM inspector and I can see what edits need to happen in Denver to make that data better. So that's another tool. There's a handful of tools that are all community developed to help kind of direct mappers assign tasks at random, either identifying issues programmatically, or in the case of humanitarian mapping, identifying an area that is in need. And the feedback loop there's certainly an active area of research to be done. Is what is the feedback to these contributors working in these areas? They choose these tasks. What is you can do change set comments and stuff, and that's another area to look at is how are new editors especially almost being treated in terms of the response and the comments to their edits, and how is that influencing? And so there's been some work with that. Martin Divis has been looking at that in like disaster mapping, which I think is really interesting, but also a lot of community tools to try to, when mappers mapping somewhere, to also try to show who else is mapping that area, and create kind of local communities from the map that way. So yeah, a lot of these are kind of new tools in the last 18 months to try to get at that.
So my second question related to that, the disaster mapping, and what kind of time scale are they? How would you quantify urgency? What mapping task would be like so urgent and to be done now versus things that can wait? Yeah,
so it kind of depends on the disaster and how what needs to be mapped. I mean, in the response to the earthquake response, especially, or I guess with floods and typhoons, it's usually a little bit more warning. And so you see different kind of ramp ups in mapping activity. But like with, and so the task manager, for example, the OpenStreetMap team is really good at labeling tasks that are out there as urgent, critical, and lower moderate. And so that can help direct people to mapping. But we do see kind of like the Monrovia example, Monrovia, Liberia, that all those edits kind of happened over the course of the year. It was a long activation event as that outbreak was a very different type of disaster.
Is there any task that in the really short turnaround time frame, time critical, like an hour? It needs to be done within an hour. Otherwise, it's useless. And can you think of any example? I'm just kind of wondering.
Yeah.
The boundary of
I mean,
what is the example of the most urgent task we are aware of?
Yeah, probably.
And what's the time scale? What are we talking about?
I mean, sooner the better. I guess the most, that I've observed is definitely like the Nepal earthquake response. That was probably the most immediate. There was people responding, disasters, responders on the ground that didn't have maps of what they needed to be, where they needed to be going. And so, the more immediate you can get that data in, the better.
So it's like days, but not minutes, right?
Not minutes, but we can strive for it. That would be pretty cool.
Some of that's dependent on the companies that donate the satellite images.
Exactly. So that can be another
The
complication.
speed of the satellite image can be made available.
street satellite image can be made available so you can get the satellite in position to take the image. These types of things.
Also, all this just building up to my last final questions. It is about technical question about your code for real timeness of your processing. And then, so if the time scale we're talking about is like a day, or even just within an hour, so what is the target real time? So are you talking about a minute or 10 minutes? That's what you're capable right now, right? So it's more like near real time. Can you be more precise in the real timeness?
Yeah, so that was something that kind of we went away from after the Nepal earthquake. We were computing that every 5 minutes, and then we had to start delaying that to 10 to an hour as more data was being ingested. Currently, in place right now, like there's a leaderboard tracking all of the humanitarian editing with the Red Cross to the Missing Maps program. That's running on the OSM Mesa utility, and that's crunching data hourly. And so that's, I think, currently where real-time analysis for OSM sits. But that's a lot of pre-computed statistics, number of buildings per person, per task, kilometers of road, mostly those two things. And so that's currently where real-time sits, and this is definitely a very open-ended question that Seth and I have been talking about a lot, the maintainer of that system, is what does it look like to compute that history, to be able to compute that history to be real-time, and that's still a very open-ended question of what that resolution is. We'd like, I think anything within an hour is probably good enough to let people kind of track that response.
So the current technical approach that you've taken, which is great, is a software engineering approach using map reduce. Basically, just for more machines, but you figure out a way to divide them into tiles to be able to compute highly parallel, massively parallel processing. And I'm kind of curious about another approach at an algorithmic level. That is there any computation that can be made incremental? Instead of the compute, is there any need to carry out incremental computation, for instance, based on deltas?
Yes, exactly. And that's our approach right now to one approach we're thinking about, especially for real-time work, is if you first segment it out into tiles, right? Then not all 2.5 million tiles are being edited every hour. And so tracking that better in terms of how we're ingesting the data, and then being able to do more incremental analysis of just where the map is changing. That's currently not really happening, but that would be a major approach.
So I'm getting really concerned about time.
I'm done.
I'm sorry. Okay.
Yeah.
Are you good?
Yeah, I'm good.
Okay.
Thanks.
Great. I'm getting concerned about time, so we're going to move over to Brian, who's going to ask next set of questions.
Okay. So I'm going to use Wikipedia as a reference point, which probably is not surprising to you. So Wikipedia, a lot of activity, increasing that activity in Wikipedia is actually going on behind the scenes instead of the actual production of the things that people consume. So how is something like conflict managed between mappers and OpenStreetMap? And how do you sort of trace that kind of activity in this sort of human-centric approach that you developed here?
Yeah, I guess can you give an example more of conflict?
So if you and I disagree with this road should be, we're going to be sort of hash that.
Yeah. So I mean, right now that's just the latest evidence, right? Okay.
All right. So the short answer is so in Wikipedia there's an anxiety that a lot of this sort of activity for coordination, communication, distracting from the substantive actions and producing the artifacts. It sounds like OpenStreetMap's people are just the work is just mostly on the artifact itself.
Yes, and then there is the data working group, and they will go in and revert things or kind of come in and settle that dispute if needed, and that happens at kind of the board level, overseeing the organization. But much of the discussion then just is hashed out in the mailing list,
So then my next question is so in your dissertation you sort of touched on some of the anxieties around sort of the increase around corporate editing. So I want to connect those anxieties with sort of social computing after 2016. So what sorts of institutional guardrails exist to prevent bad faith editing from happening on OpenStreetMaps? So you gave the example like putting like the right turn light signal like on 28 and Colorado. If someone goes in and turns that to like a left turn only signal, like what kind of like, so this relates to information quality, this relates to corporate editing. So like if you had bad faith actors trying to manipulate OpenStreetMap to make it have like bad information to like break things that people depend on, so how do we sort of like build tools to monitor that? How does the community handle that right now?
So one thing that's quite interesting in the nuance of corporate editing is that, so there are a handful of tools that are constantly monitoring what the changes are and exposing, and basically tools to let people review edits quickly. And these tools are, for the most part, produced by corporate entities that then want to use the data, and that's kind of their validation process. So one thing about corporate editing is that that I want to really investigate deeper is these corporate edits, do they represent this like last 10% of the map validation, and is that what they're really providing to the map as opposed to like a corporate takeover? I think that's a really good open question. But so there are utilities that are allowing people to go through and like look at those edits as near real time as they can, so that they can be ingesting the best data. But this is also a concern of like, how does that scale? Does that just mean Apple hires more people to sit there and look at these tools? Or what does that look like? And how do you capture very specific types of changes? This is something that the community has definitely grappled with over the last year.
So two more questions. One is that you've like focused on crisis mapping as like a very important input into like the ecosystem of like sort of getting people who are in Germany to come over, start editing Haiti and things like that. In your experience, like both like building these systems and looking at the practices of people in the systems, have you found like are there other kinds of disruptions that happen in the social system that sort of like cause people to sort of get outside of their editing sort of habitus, and like how does that sort of like suggest or make, how does that sort of lead to recommendations for this community for like getting people to like share their expertise and smooth out these like very skewed participation distributions that you described?
Yeah, so certainly I've been most focused on disaster mapping, especially that with the humanitarian OpenStreetMap team, as definitely the largest organizer of those types of events. Another thing I guess I can say with confidence in looking at the data is that these types of events are bringing in the most, the Haiti example was interesting because, and this was also part of that other Finding the Ways paper, a lot of those first mappers were existing community members. There wasn't that many new contributors in Haiti, whereas opposed to now, disaster mapping is bringing in, it's a major kind of introduction tool to OSM to bring in new contributors, and people are being introduced that way, which is changing the signature in the data entirely. That used to be a way that you would calculate where someone's first edit was probably where their home was, and that's just not true anymore. Where someone's, the concentration of someone's edits, if they're joining for humanitarian mapping, is going to be most likely not their home. Other activations, just like personal experience of working on this Denver building report, like we are getting a lot of newish contributors participating in that, taking ownership of the local area with that. So definitely seeing that's going to be definitely also a very different signature in the data. Other than that, yeah, I've mostly been tuned into the disaster mapping, but like I said, I think there's going to be more communities that are going to kind of continue to pop out as we have these tools to dig into the map. And certainly still localized hobby mappers or local editors are still also leaving a very distinct impact on the map.
So my last question is, so I'll put get on my soapbox and then get back off. So on the soapbox, like a lot of like the sort of defined Western civilization for like in the 15th century to the 19th century is the existence of commons, where we also like contributed or drew resources out of something, and then you had this enclosure movement where we closed off the commons, introduced private property, introduced capitalism, and like we've had a whole host of like bad things happen after that. All right, so back off the soapbox. So OpenStreetMap is an example of an information commons, and you're seeing with these corporate editing, like these anxieties in the community around, like, are they taking ownership, or they having undue influence? So is there a risk of like enclosure on this in OpenStreetMaps or more, so my more specific question is, what role can like human-centered technologies play in like sustaining like a robust information commons, like the tools that you're building, the communities that exist, like how do these things all like interplay to sort of like support a robust commons, information commons where this information that we're all producing and sharing remains open and available to everyone?
Certainly, monitoring and accountability. I think that these tools allow us to monitor this activity at scale. Whereas, a lot of discussions, Facebook has been super active in terms of like, what I didn't even talk about is all the machine-assisted mapping that's now happening in OSM. That's really the hot research topic just coming out in the last year. Really, is how can we use machine learning, machine vision on these areas to then increase the data, and that's really being led by the corporations trying to increase the amount of data, and that's got people all sorts of freaked out for good reason. And so it's a matter of monitoring and measuring. I think that's really where the human component is and comes in, and then the interpretation of that, right? Monitoring that, but not just looking at data depth, but what's the interpretation? What's the how is the corporation or the group of mappers interacting with the other communities, the rest of the community? Are these companies giving back at a scale consistent with what they're kind of extracting from the map, right? How valuable is this data to them? Very valuable. Are they also contributing back in that way? So definitely just, I think, monitoring. I think that these tools can help us get at those aspects. Great, thank you.
I think what's interesting about the corporate thing is that, ultimately this all comes down to the real world. And all the companies have customers that they want high accuracy for the tools that they deliver built on that data. So it's not like Apple's going to go in and mess things up for Facebook because they'd be messing things up for their own customers. So there's an interesting constraint there on their behavior if they're going to have their customers. Anyway, I just want to comment on just a few things. I love the trajectory of this work. Epic OSM, as you said, was designed here in Colorado. It was actually designed at that table right there with Robert, Marina, you, and me doing that independent study. One thing I think has been really amazing to see is I remember asking you questions along the way in various presentations about, well, that's great. You have annual snapshots. Can you have, what other types of granularity can you get? And so to see you in this dissertation get all the way to full representation, that has been a goal for a long time. So it's just thrilling to see that it's there. And I think building on what Tom said, I think now you've got if I wanted to ask the what have you done for me lately question, it would be this closing the gap to real time, and how do you get to the point of both processing the incremental changes and setting up the analysis infrastructure to be able to answer things in seconds after edits have shown up. So it'd be really interesting to see where your work with Seth is going in that regard. 22 seconds query time in Athena is pretty good, but you still have a whole order of magnitude on that. I think maybe comment just a little bit on that, and then I have one other question after that. So what do you see? What do you see some of the next steps would be in terms of tackling that?
It's I think that's a funny thing with big data is the limitation there with like that processing pipeline in particular then kind of just comes down to how much money and resources can you throw at it.
Right.
It's like, so if we can run a 1,000-node cluster, we can be ingesting data and we're computing that at that scale. So that's kind of one approach. I don't think that's like the most novel approach, but that's definitely one approach that we're kind of looking at. How can we, and a few more kind of tweaking the data representations of how can we get more of that incremental piece.
Does the OpenStreetMap community itself or organization have the resources for that sort of infrastructure?
So they do. The public API does have minutely diffs, and that's kind of the standard. So you can be consistently ingesting the minutely diffs to the database. and that infrastructure has had to scale over the past couple of years as well. So that's kind of what you can shoot for.
Yeah, if I reflect on where Epic has gone in its infrastructure to analyze Twitter data, we're arguably we had to have millions of dollars and about $40,000 computing equipment to get started and do what we need to do. And now with the work that Gerard did for his master's thesis, we're down to $200 a month on that infrastructure for very scalable. So things just all in the cloud. So I think that's actually a very interesting contribution, is to be able to say, to do this stuff, now we're looking at hundreds of dollars, and if you really want to do as fast as you can, then companies can kick in up to thousands of dollars and be done. The other thing that I think was really interesting was this notion of taking the relations, the things that are invisible otherwise, and finding ways to translate them into the data so that they then become queryable.
Yeah.
And so that was a great example of the, find the intersections of those relations and then put that on the map so that you can query it. Are there other types of relations that are amenable in that way?
Yeah, the big thing is, so relations can also represent the complex buildings like multi-polygons, but the tools to turn that into GeoJSON have improved over the last year, 2 years as well. So we are getting those captured. Relations can also be like, country outlines. Those are also being included, I think, as large multi-polygons. The other big one is like routes, like bus routes, for example. That's one way to represent all that data. Is okay, so here's the road, and then there's a bus stop, and the other road, and so there's a lot of bus routing. It's going to have a slide that shows just like all the bus routes in the world of the map. It's an impressive amount of data.
Right.
And so those aren't currently being represented in QA tiles.
Okay.
And so that's another example of something that I was more concerned about, the coverage completeness with the term restrictions. That was like an open question people have been talking about for a long time. And the conversation really got stuck with, how do we represent that? How it doesn't just belong on its own object, right? Because I'm the one trying to come at this with the one, I just care about metadata. And so that conversation got stuck for a while of, well, how do we represent this? This should really be this thing. Should we move to a different type of relation with GeoJSON? We can get this topology, like it doesn't belong on its own object. And so you can go read the whole GitHub issue report on that. And finally I was like, no, I need to count this. And actually it was after making that first corporate, the kind of hockey stick chart showing the growth. And someone from Telenav reached out to me and was like, this doesn't seem right. And I just computed it with the latest snapshot. I said, I think we've done a lot. I know we've done a lot more activity than this. And I said, okay, this is interesting. This is definitely a problem with how the data is being represented.
Right.
So that's when I just implemented that. Said, okay, I take the metadata, made the OS and QA tiles plus, and regenerated that. And suddenly Telenav's edits were like, whoa. And because they were doing a lot of term restrictions. And so it's kind of funny to see how, they felt that in reality, they measured up higher than some of the other companies. So that was something
Taking
like
invisible, make it visible.
Exactly. So
Wonderful. So the great thing about doing this the way we do it is Jennings gets 3 rounds of applause. He already got one. Now he gets another for after finishing the questions from the committee. So let's do another one. In the back room here, and you get to ask questions. And if you want, give him a 3rd round of applause. So
it's in there.
okay, awesome.
Yeah.
Hi.
Hey.
I have a question about potential future work possibilities, I think.
Yeah.
So as you know, one thing I do is try to provide geospatial data sets to people.
Mhm.
And it seems like with this contributor-centric analysis that you've had, with all the caveats of different 0-15 tiles being different sizes, it would be really interesting to build a metric for each one about what that data quality is, considering OSM creates geospatial data for areas that don't have it. And so I'm curious about what you think the viability of doing that is. An example being that like 15 different contributors and that one tile being a step, and then like who those contribute. Does that, have you?
Yeah, and I guess the closest to that would be like
That's kind of what this is doing, using the annual snapshots, and then there are, I have computed that for like 80 different cities in the world, kind of showing exactly those metrics. I didn't show that here. The big question with that, when you get to global analysis, is normalization by population.
Yeah, so if you can build a tool that lets somebody that's just approaching it have some sense of that data array, that depending that a quick way of going to a QA file and being like, yeah, this is going to be solid for this kind of data analysis.
Yeah.
And I don't know if there's, I mean, this is great, like being able to go here and just seeing the tile that you're working in being dark blue, I guess, but how many different facets go into that, I guess? Depending, like, so that can scale depending on the kind of research that person is doing with that geospatial data.
Yeah. So a big question is, what are the needs for what attributes get computed ahead of time, right?
Yeah.
And rendered. So like this dashboard, for example, we have building density, number of contributors, kilometers of roads, handful of other kind of pre-computed metrics. But that's another thing that I think is a powerful tool would be, not all needs to be pre-computed and then rendered and visualized. The ability to kind of submit, this is the attribute that I want to know about, and then how can that go into that pipeline. Big thing with that is we will be able to get to that by going to kind of more cloud-based implementation. Currently, another thing I didn't mention is that my whole approach depends on, by using the OSM tiles and using the snapshots, I'm not running any other major infrastructure. So there's not a database backing this. There's nothing that's up all the time. So when I run this analysis, I can stand up a machine and just run it and get the output and turn that machine off. And so it's scalable to that end. But in the future, going more real time and being able to dynamically change these attributes people want to know about, certainly will need to go to more like the database cloud and big data model, which is the direction of most interest. It's just a lot of question about time to develop it, funds to develop it, who's hosting that. That's good.
Because it just strikes me that, especially from that global perspective, like building this tool that people that are doing research and want to access this database can go in and check and just be like, this is awesome.
Yeah, and so what currently happens is there's probably 15 different kind of single purpose maps and tools out there answering those questions for those different purposes, depending on who does it, and then a whole number of internal tools used to have people doing similar stuff.
Yeah. So you mentioned now we're not at corporate takeover level yet.
Yeah.
Could you just explain a little bit more what you mean by corporate takeover and why that is concerning?
Certainly. So a lot of people like the beauty of OSM, right, is that it started as this volunteer gold map of the world. It initially started in the face of difficult to acquire geospatial data owned by governments, difficult to have a license to use the data, and so that's what it started as, and then it's grown into a lot more, and it's grown to the point where companies now really want to be involved because it is the best source of data in many parts of the world, and so rather than Apple or someone putting resources and sending someone to these parts of the world while they walk around with GPS, they can just bring in, they can just use OSM data. And part of the beauty of OSM is the open database license, which says that data can be used for any purpose, really, as long as you have attribution to the contributors. So using data in that way, showing attribution is totally okay use case. I think that when that was maybe put in place, people haven't thought that it might be used at these scales with some of these companies. It's really new. And I think that, the big concern would be like, it's this project that allows people anywhere in the world to kind of have their own map and represent themselves in the map the way they would like to be represented. And if Apple comes in first and just like maps it all from satellite imagery, is that local community of mappers going to develop? That's a great question. That's something I want to investigate further. So I think, yeah, people just feel, I think, definitely threatened that like the interactions with that mapping, that if the corporations are going in or being paid to map it, it just changes the product entirely, rather than like volunteer organization. Right.
Could you talk a little bit about like any possible geopolitical implications of this kind of work? So, for example, I'm thinking about, I don't know if your analysis, the contributor-centric method, is able to do this, but identifying possible contractors for governments who might be mapping for military purposes or that kind of thing, and then what does the open source community accountability do against those, kinds of forces?
I think we could start to identify some similar things. I know that any mapping that's happening specifically for those purposes isn't necessarily happening on OSM, but on kind of more, other more internal kind of lockdown version of OSM. But we could definitely start to identify some questions like that. The other great question is borders and such, right, as they're changing and how they're represented on OSM. And I guess it's like last edit kind of wins, right? How things get moved. So that's certainly something interesting. A lot of the data then, it's funny because what happens like on OSM.org, there's just one version of the map, but that data itself, as that's rendered, isn't necessarily being put into these other products. That data is being consumed by other people and then redistributed into a product like an app with a map. Making digital maps of the world means that depending on where someone's viewing that map from, they might see a different map, and that's just kind of how that works. So that's something that people definitely are doing with OSM data as well. So yeah, there's a lot of nuances there. The patterns we can extract from the data that be interesting to see what other kind of patterns pop up. B.
You said OpenStreetMap started with the goal of like mapping the whole world. Has there been any areas that are finished in any sense? Like all the graphs, like you showed the users and the edits are still going out.
And I mean, kind of the joke is like Germans are now on to mapping blades of grass because the map is extraordinarily complete. Like it is the most complete map, just very active community in certain areas. Certainly, it's gonna that coverage is gonna vary. The map of campus is fairly complete, but this gets at like a fundamental question in geography is like there's no such thing as a complete map, right? Like, by definition, it's an abstraction of that. So yeah, there's certainly it's different. It's kind of different all over the world, and is at varying levels of completeness. But certainly in many places, it's the most complete. But it's a really initially that seemed like that was the question you wanted to ask, and then it was like, oh, that's a really hard question. And we can quantify the data places, but trying to get at if it's complete or not is certainly kind of comes with its own set of complications. If that makes sense. It's a little bit of cop-out.
And the world is trying to represent is not static either, right?
Precisely. Yeah. No. One cool thing is that once the world's completely mapped, and then like will OSM update at a rate consistent with how fast the world around us is updating, and it's like that's kind of cool.
I'm picturing some mapper in Germany hanging outside of an abandoned storefront and waiting for the next people to move in so they can change the app. I can change something.
Are climatologists using this at all for predicting or being able to map where the disasters are likely to occur is, given the politics of not doing anything.
Certainly, I'm looking at Robert, he's nodding. That's Robert's area of expertise. And certainly like the big point of OSM, or a big use of that is like we, in terms of, well, there's many ways to get from population density, but also built infrastructure. And you can use OSM data to get at, to understanding kind of where built infrastructure is and how much is at risk. Certainly this data is being combined with many other data sets to kind of answer that question. But it is a valuable data source of that, especially more vulnerable parts of the world where this is going to be kind of the only map, and then becomes a critical data set to add to the other natural features that we know we're adding to kind of build infrastructure on top of that.
I've got a more general question. Sorry. The data that we supply in disaster events, like so OSM, the way they use it, so everyone contributes from across the globe using satellite imagery to trace roads and that. So say you need to get to a village to deliver supplies or something. So they need that data so they can get there, like know where the road is. But what if the road gets blown out or something? Like the earthquake shatters the road, and so like other people on the ground contributing information saying, hey, that road is no longer accessible. Is there temporary features where you can edit the maps?
Yeah, so there's been a lot of questions about like how do you get the temporary, what belongs to OSM and how do you do that? And so I think there's many of those disaster areas. OSM is then just going to be the base map, and then on the ground information will be put on top of that. And so that information is being contributed in those ways. There's a lot of buildings in Haiti that are still mapped as building equals yes, collapse equals yes. And that's something that was like identified from the satellite imagery. And yeah, depending on using the most updated source of satellite imagery, especially in mapping around Boulder, it's like, okay, you got 2017 imagery, that's fine. But in a disaster, it's like, oh, is this yesterday or is this 3 hours ago? That imagery matters. So there are different ways in how that data can get represented in those temporal pieces, but I think typically that's done kind of more on the ground. I think a lot of those like paper maps are marking that up from that OSM data as well. So there's all different ways that this data gets consumed and used in those situations. Robert.
So when we first started this work back in 2013, we were kind of stuck in that we kind of couldn't even imagine some of the questions that we would want to ask. Because it was just so hard to do. And I feel like we've made a lot of progress in terms of our ability to ask better questions, to know more things. I'm wondering what's your evaluation of how much progress we've made in terms of knowing what questions we want to ask, and where, and what sort of things should we be doing moving forward to find out what those questions could be.
So that's fun. I'm going to go kind of meta on that for a second. That was what so when we first sat down. We tried to come up with a list of all the questions that we want to be able to ask, and we tried to design that for OSM to be able to ask those questions, right? And I think where we're at right now, we've been able to answer a lot of those questions, but also I think with some of those answers came like, okay, what does that mean now? Like, what's the next step? What does that imply about the map? And I don't know that that's the response that we expected to get out of those questions. And so I personally kind of shifted away from the question first, let's build the infrastructure, and ask it to say, okay, we did that. Now let's push the infrastructure further with not really a set of defined questions, but just like, oh, could you represent that? Could you map that? And the question is like, what are now the questions? Then we can look at the data, and can we derive new questions from that? And I see that as kind of being the point we're at right now, which I'm pretty excited about. So I think we've come a long ways, but it's hard to quantify.
Congratulations. You know me, I like to make jokes. So Jennings, my only concern is every dozen. That's amazing. Fantastic work.
Can I already tell you?
Yes.
Oh! So, congratulations, Dr. Anderson. We'll let you rejoice a little, and then we'll do some photography, and I'll finish signing some paperwork and stuff, so. Zhao, thank you again. Okay,
Thank you, John.
bye. Thanks for your job.
There's your round of applause. Breathe now. No, this is awesome. You see the progression. See, because I sort of had snippets of what you were doing this last few years. I didn't,
Yeah.
just to see. It's pretty impressive.
Yeah, you want those data sets now? I promised those to you like 2 years ago. You can have them now. They're ready.
I just now need to hire a student to work on this.
Yeah.
Sure, I've got one.
Okay. Thank you so much.
Congratulations.
Thank you. Yeah, we're done with that. Actually, was there any questions?
Sorry,
people said we're
I walked right in front of it earlier.
No, you're fine. Then just click end.